All right, so I'm Sam Lefforge, and my mentors are Dr. Sharma and Dr. Lee. And my project was over the automated detection of gas signatures using fiber optic sensor data. So when drilling for oil, sometimes methane gas can make its way up into the oil rig. And this is extremely dangerous because methane gas is so flammable. Just one spark can cause a massive explosion. Which is exactly what happened on the Deepwater Horizon, which ended up costing 11 lives and resulted in an enormous environmental disaster. So obviously preventing this is a super high priority and has a lot of benefits. So that's what our goal was with this project. The method of detection we wanted to go for was fiber optic sensor data, uh, which uses fiber optic cables distributed down within the well to sort of detect the some acoustic data from the gas as it rises up. So this allows us to have sort of a position and a time for the gas, which in turn allows us to calculate its velocity, which is extremely important because knowing the velocity of the methane gas rising allows an operator to know how much time there is before the gas reaches the oil rig, um, which is important for making decisions like whether or not they should evacuate or whether there's something they can do to salvage. And the data was actually collected on the LSU campus from the wells that they have there. So the data that I was working with came in the form of very large matrices with depth and time, and each cell shows the acoustic sensor data for that specific depth and time. And I actually worked with the Fourier transform output of the original data. But for the rest of the presentation, you're going to see this data represented as an image instead of as a matrix. And this is because representing our data as an image allows us to use various image processing techniques to detect the gas signature, which you can see here as this sort of diagonal line in this image. So the first image processing technique we used was called Sobel edge detection, which is where a filter passes over a grayscale image. For this slide, I use this example of a laptop, but this is just to demonstrate sort of conceptually the workflow that was used on our data. In practice, this image of a laptop would actually be an image of our data. But for each pixel, there's these filters are passed over, and what these filters do is take a weighted average of sort of the 9-pixel range around any given pixel, and then they're combined using this equation over here, and you end up with something that looks like this, which shows pretty clearly the edges. But there are still some gray pixels in there. So after this stage, just a simple threshold is used to produce a binary image where every pixel is purely white or black. So here's a little program I wrote just to sort of visually show what's going on when this is happening. In the top left, you can see that red dot scanning over the image. That is the mesh checking over all these ranges of pixels. And then at the bottom, you can see GY and GX. GX is detecting those vertical lines, and GY is detecting those more horizontal edges, and they combine to produce this image G. So once you have the binary image, we need some way of actually finding these lines and their equations. And so for that, we use a Huff transform. Down here, you can see this GIF. There's this sort of spinning line, and that's representing how the Huff transform passes over each pixel on this image, each white pixel, and checks a whole bunch of different values of theta. So you can see as this green line is spinning around, checking all these values of theta, it's calculating a value for rho for each of these using this equation here, and then it's graphing that over here on the left. You can see this red dot moving across is doing that. And so the final output of this is something that looks like this image on the right, where you have this image that graphs rho and theta, and you have all these streaks sort of going across the image, and each of these streaks represents 1 pixel. And where these streaks cross, where they have like very large intersections, those are where your most prominent lines are. So what you can do here is search for the largest number of intersections, and then you can say, okay, the theta here is this amount, the rho is this amount, and you can then turn that back into a line. You can think of rho and theta sort of as a slope and a y-intercept. So once we have these lines detected, we need some sort of method of evaluating them. And one way of doing that we use is just by looking at the pure number of intersections on the Hough transform, or visually sort of the brightest areas here. But another method we used is looking at the average distance between a line and all the other lines. And this helps us to sort of eliminate outliers from this group of lines. Like you can see this dark line over here has got a very low score, in part because it's so far away from this actual cluster of lines that represents the gas signature. So on the field, the data, you don't have the luxury of working with entire data sets like I've been doing earlier. The data comes in live, so you have to work with just a few seconds at a time as it comes in. And so that's what I tried to simulate here. I basically fed the program sort of, a 10-second chunk or so, and it calculated what it thought the most likely line to be the gas signature was, basically by taking a weighted average of all of the lines detected with the Hough transform, weighted, of course, by the evaluation that I described on the last slide. And so you can see here for this live data, early on, it does a good job of detecting the gas signature. And then as I continue to feed it more data that's just random static, it starts to guess basically just random lines, which is expected at this point. And so here is another example of the same thing with a different data set. You can see on the left, this signature is a little more subtle, but it still does a pretty good job. On the right, the signature here is pretty hard to see, and there's a lot of noise going on in the background. And so here the algorithm failed. So there's certainly still room for improvement with how I'm going about this. This is a video that I made showing sort of what it might look like for an operator looking at this data coming in live. You can see at the bottom, it's calculating the estimated velocity for each of these lines. And you'll notice that that velocity sort of trends upwards as the new data comes in. And this is also expected. As the gas rises, there's less pressure being exerted on the gas from above, and so you expect it to accelerate, which is important in determining factors, questions like whether or not you have time to evacuate. So in the future, I would like to implement an evaluation of this data when it comes in live. I mentioned earlier that I have a method of evaluating the data of the whole set. But of course, when it comes in live, it'd be useful to have some sort of metric that shows whether or not that there is a threat of methane gas rising. That way, an operator wouldn't have to manually look at the detected line and determine that for himself. There's also a couple methods that you could approach this problem entirely differently from the way that we did it. One of those being convolution-based line detection, which uses, if you recall earlier, that the GX and GY produced from the Sobel edge detection, the relationship between those can be used to find a directionality for the edges, which eliminates the need for the Huff transform altogether. And a very different approach would be to use machine learning, which would entirely eliminate the need for any sort of image processing. And this would be useful because when you convert this data to an image, you introduce a little bit of ambiguity. You can see these two images represent the same set of data, but they look entirely differently just because of for each of these images, I went about converting them to an image in a different way. So the reason that we decided to not go with either of these approaches is that we were working with a very limited data set, and these methods won't really work very well without a very large data set. But certainly in the future, when more data becomes available, these would be a more robust way of approaching this problem. All right, that's what I've got. Are there any questions?
No questions? So do you think this could be applied to other phenomena where, you know, something is moving fast or?
Yeah, I think so the data that I was working with is, of course, it's gotten from fiber optic sensors, and this in theory could work with any sort of fiber optic sensor data that where you know sort of a certain frequency that you're targeting, and you know this method of edge detection and line detection, I think, does have applications well beyond you know, gas signatures, you know, for all sorts of fields.
Yes, sure, yes. Any other question, comment? Okay, if there are no more questions, let's Sam. Thank you, Sam.
Thank you.
Okay, next speaker is Adriana Maswell. So wherever you are ready.